Another interesting phenomena that we usually discuss when talking about light is sunset, sunrises, color of the sky, color of the sky at noon, all of that. Now, okay, let's look at these pictures. You notice from here, for example, that what we see a reddish color of the sky at this time. We see it here as well. Now, at this end of the sky, it's more bluish. We see the same thing during a sunrise. See the reddish color of the sky. Now, at noon, though, when we look towards the sun, the surrounding sky is more blue than red, and the sun itself looks more whitish. Now, why is that? Now, again, this is not like in the case of the aurora. This is not due to simply refraction of light. Now, if you think of the Earth as the sphere here, and the atmosphere surrounding the Earth, the atmosphere is made up of particles. And actually, that's why you have more spectacular sunsets when there are weather events or when there is more dust in the sky and sometimes even pollution in the sky. The atmosphere is made up of particles. It has molecules in it, and then what other particles are available in there. Now, these particles are going to scatter light. And as they scatter light, they are going to scatter it differently based on the wavelength. The relationship between the intensity of the light scattered and the wavelength of the light is this kind of relationship. It is proportional to the inverse of lambda to the fourth power, which means, if you look at it this way, the shorter the wavelength, let's talk for example of visible light, the shorter wavelength, which is blue, is going to be scattered much more than the red light, because it has a shorter wavelength, and remember we have this huge number in the denominator. So blue is going to be scattered much more readily than red. So what does that mean? If I have the sun here, white light emanating from the sun coming in this way, what this means is as the light interacts with the atmosphere, more and more of the blue component of that light is going to be scattered. Being scattered means it's not going to continue along that straight path. If it's not going to continue along that straight path, my light beam is going to start lacking more and more of that blue light. And the more of that blue light is going to lack, the reddish the color of the light is going to become. Now that's why it's going to be red, more red here than here. And that's why during noon, when the light is shining from straight across, there is less atmosphere here, so less particles, less blue light scattered. That's why it's going to look more whitish. In the same token, when light is being scattered, so the straight light from the sun is going to look reddish or whitish, but what we are going to get from here is the scattered light, and that's the blue light of the sky. That's the blue color that we see of the sky. So it's not simply refraction, it is more due to the scattering, and actually the term for that is what we call Rayleigh scattering.